Hello, welcome back. In this last lecture on branch and bound, we will revisit a problem we briefly touched on before. If you recall, we introduced the 0-1 knapsack problem while discussing greedy algorithms. We know that greedy cannot guarantee an optimal solution for the 0-1 knapsack problem. However, it can solve a related problem, the fractional knapsack problem, in polynomial time. Today, let's talk about the 0-1 knapsack problem and its branch and bound solution. Given a container of a certain capacity, either mass or volume C, and a set X of n items, each of which has its mass and value, our goal is to find a feasible subset of X such that its total value is maximized. A subset S is feasible when its total mass is no greater than the limit C. 0-1 here means that we either include an entire item or not include it. So it's either 0, not selected, or 1, selected. Some observations on this problem. The decision version of the 0-1 knapsack problem is NP-complete. Therefore, no polynomial time algorithm has ever been discovered and likely never will be. There are also no greedy algorithms that can guarantee to find an optimal solution to all instances of this problem. Now we have come to our last resort. What about branch and bound? We know the complexity of this problem is exponential. Can we use branch and bound to reduce the enumeration of complete solutions? In order to provide a branch and bound solution to the 0-1 knapsack problem, we need some preparation. First, the framework of branch and bound we have seen so far works for minimization problem. However, the knapsack problem is a maximization problem. How can we convert it? Second, to create branches of partial solutions, we need to figure out a representation of a candidate solution. It needs to be a sequence of decisions. So when we use branch and bound, we can extend a partial solution one decision at a time. Third, how can we compute the lower and upper bounds of each partial solution? The answer to the first question is in fact quite straightforward. We can add up the values of all items in set X and use that to subtract the total value of items chosen in subset S. We can call this the total value margin or just the margin. Therefore, maximizing the total value of the subset S is equivalent to minimizing such a margin. For the second question, a natural and intuitive representation will be a binary string of length n, where each bit indicates the choice on one item. A 1 means choosing that corresponding item and a 0 otherwise. In the example here, 0, 1, 1, 0 means given 4 items in the set X, we choose the second and the third items to put in the knapsack. For the last question, remember we developed a greedy solution to the fractional knapsack problem, where we sorted all the items in a descending order based on their unit value. Then we pick as much of each item as possible within the total capacity limit C. The fractional knapsack problem allowed us to take any fractions of an item, which the 0-1 knapsack does not. However, the greedy algorithm still serves as a good heuristic. Let's see how it works. Here is the idea. Given this example here, we have 4 items, A, B, C, D in total. We sort them based on their unit value. The capacity limit C is given 15, and then the total possible value is 10 plus 10 plus 12 plus 18. That's 50. Now our goal is to choose a subset of those 4 items and to minimize the total value margin. We represent a solution as a sequence of 4 decisions. What are the lower and upper bounds? Recall that we need to minimize the total value margin. So the lower bound is 50, 50, that's the total possible value, minus Remember how the greedy algorithm worked for the fractional knapsack problem? We take as much of A as possible. A has a total mass of 2, so we can have entire A. And then we can have entire B, that'll give us a value of 10. And then we can take entire C. Can we take the entire D? No, we cannot. So we use the unit value of D, that's 2. Let's see how much capacity do we have left. So the capacity limit is 15 minus 2, that's the mass of A, minus 4, minus 6. So this will give us the value of 12. This is not a feasible solution for the 0-1 knapsack problem. However, it serves a solid lower bound because we cannot have anything that's less than 12. What about the upper bound? We can use the similar greedy heuristic without taking fractions of an item. So this is the total possible value, 50, and we take entire A, entire B, and entire C. Can we take entire D? No, we cannot. So that's all we can take. And then this will give us the value of 18. That's the upper bound. Okay, so this lower and upper bounds are the initial global lower and upper bounds. Now let's look at the first decision. That's for item A. We can either choose item A or not choose item A. When we make sure that we choose the item A, the upper and the lower bounds will be the same as the global upper and lower bounds. And for this solution, we use the same greedy heuristic. So that's 50 minus, we need to come up with a feasible solution. Now we're not picking A, so we'll look at B first. We'll pick entire B, that's 10. Can we take entire C? Yes, we can. Can we take entire D? No, that'll exceed the capacity. So that's all we can take. And then the upper bound will be 28. What about the lower bound? We'll use the fractional knapsack greedy algorithm. We have 50, that's the total value. We take as much of B, we take entire C, and let's see how much of D can we take. So the capacity is 15 minus the mass of B is 4, the mass of C is 6. So this will give us a lower bound of 18. Now let's check the bounds and see if we can throw away any partial solutions at this point. No, we cannot. Now, out of the two partial solutions, which one looks more promising? It's the one on the left-hand side. So we'll keep extending this one. For the second decision, we have two possible values as well. It's either 1, 1, or we have 1, 0. When we have both items A and B in the set, the upper and the lower bound will be the same as the global bounds. And for this solution, so for the upper bounds, the idea is the same. We need to come up with a feasible solution. So we'll choose A, that's 10. We're not going to choose B. And then let's move on to C. Can we have the entire C? Yes, we can. Now what about D? Can we take D? No, we cannot. This is the best that we can do. And then the upper bound will be 28. For the lower bound, we use the greedy fractional algorithm. 50 minus, so we take the entire A, we take the entire C, and we take part of D. So that's the unit value of D, and see how much capacity do we have left. So 15 is the capacity limit minus A's mass and C's mass. Okay, so this will give us 14. Now let's check the bounds. Are we able to update the global lower and upper bounds? We cannot. Can we throw away any partial solutions at this point? No, we cannot. Okay, let's keep branching. Now, out of the three partial solutions, which one looks the most promising? It's still the one on the left-hand side. Let's keep splitting this one. On the left side, we have 1, 1, 1. That's the third decision. On the right-hand side, we have 1, 1, 0. For the partial solution on the left-hand side, we have A, B, C chosen. So the upper and the lower bounds will still be the same. Now let's figure out the bounds for the right-hand side partial solution. So for the upper bound, we have three decisions made already. We're going to take the entire A. We're going to take the entire B. We're not going to take any of the C. Can we take D? So the mass total will be 2 plus 4 plus 9. Yes, we can take entire D. And that will give us the upper bound of 12. What about the lower bound? So we have 50 minus, we're going to take the entire A, we're going to take the entire B, that's the cost so far, and then we're not going to take item C, we can take the entire item D. So that'll give us a lower bound of 12 as well. Now let's check the bounds. This solution will allow us to update the global upper bound. Now we can actually have a 12 as the global upper bound, and this will allow us to eliminate some of the partial solutions because its lower bound 18 is greater than the global upper bound 12. This also allows us to eliminate this solution for the same reason. Can we eliminate this solution? No, we cannot. We have to keep this one. Now let's keep expanding the most promising solution. That'll be this one here. We can keep splitting this partial solution. We have 1, 1, 0, 1. We have 1, 1, 0, 0. So this is a complete solution, and we can compute its total value margin. That'll be 12. And for this complete solution, the total value margin is 30. So we can throw away this complete solution. Now we can stop here because we have found a complete solution with the total value margin 12. All the other partial solutions are either thrown away already or they have a lower bound no better than the complete solution we already have. This complete solution will be our optimal solution. After seeing 4 example problems, now let's summarize branch and bound. It is often used to solve extremely difficult optimization problems, typically minimization problems. However, we can easily convert a maximization problem into a minimization problem. The solution to these problems can often be formalized as a sequence of decisions, so we can branch out and extend a partial solution by one decision at a time. The key to the design of a good branch and bound algorithm is the heuristic to compute the lower and upper bounds for each partial solution. A tight bound allows us to update the global bounds and thus to eliminate as many partial solutions as possible without the need to further extend them. Although we could still be enumerating an exponential number of partial solutions, a carefully designed branch and bound algorithm allows us to throw away a substantial number of partial solutions. Comparing with brute force algorithms, where every single possible complete solution must be examined, branch and bound can save a significant amount of computation. As we are wrapping up the last topic of the course, now let's look back and hope it is easy for you to connect all the dots now. We covered 5 topics in this course, starting with computational complexity. This topic is for you to know the tools to estimate the time efficiency of an algorithm and the time complexity of a problem. We also learned what defines an efficient algorithm and what are NP-complete problems. So from now on, we should bear in mind and try to come up with an efficient algorithm in addition to a correct algorithm. The second topic is divide and conquer. This strategy is used to solve problems where the solution to the original problem can be augmented using solutions to sub-problems. The third topic is greedy, a very smart algorithm, but often tricky to design. We need to carefully think about how we want to sort the objects and how to add them one at a time. The fourth topic is dynamic programming, which share many features with divide and conquer. However, the main difference is that if subproblems repeat themselves, we use dynamic programming rather than divide and conquer. So we don't have to recompute solutions to these repeating subproblems. Dynamic programming algorithms are often very efficient in terms of time, but they require extra memory space to save the solutions to all subproblems that we have seen so far. The last topic is branch and bound, which is also a last resort algorithm when we could not find any efficient algorithms using the previous paradigms. It seems that brute force is the last option, but a smart heuristic, often using greedy, can help us compute tight bounds for each partial solution, so we do not have to investigate all complete solutions. The four paradigms we learned in this course will cover the majority of problems you encounter in the future. With the faster development of computing hardware, many people do not think algorithm efficiency is as important. In fact, it still is, and it is the defining quality of an outstanding software developer and a computer scientist. I hope you enjoyed the course and found the topics we learned interesting and useful. I wish everyone a very successful career. Take care.